Hello and welcome back to Information Storage and Retrieval. We've been a lot of places at this point. We have built a lot of different tiny pieces of a full-fledged information retrieval system. Let's recap them right away before we get into where we're heading next. So, as always, we begin with an information need, and we know that out there in the world is unstructured data, and we want to combine those into results for the user. Enter the IR system. Okay, so all the steps that we have detailed taking to some extent, some of these we can elaborate even further on, of course, but the very first step in building your system is you got to collect your documents, right? From the world, we have to define what is the set of documents we're collecting. From those documents, we got to extract some kind of text or at least some kind of information. And then we normalize all of that information into common terms, which we then chop up, tokenize them. And now we've got our documents from the world, the unstructured data. We have processed it into a form that we can now make use of for building an actual reference structure, our primary indexing step. Okay, so what are the things that we think of as primary indexes? Well, recall that these are the ones that are going to, their lists of postings are going to point directly to documents in our collection. So, term to document index, right? Term document index. Document IDs are what are in the postings, and terms are what's in the dictionary. Also, term doc ID and position. So positional term document indexes. K-gram document indexes, if we want to be able to check, these are all parallel, right? We can have all of these, but only use some of them on some of our queries. So if we ever have a search that doesn't turn anything up, we could fall back to K-grams for saying, okay, so we failed to find this exact term. I did find this exact order of letters, or perhaps not exact, but mostly overlapping orders of letters. Or we might have specialized phrase to document indexes, where we say, oh, these special phrases, we're going to actually check these first and foremost. And remembering that we can actually do phrase search using the positional index as well. But at base, we can also have the much kind of faster but more specific phrase index. So these are all of the ways that we can take what's going on in the documents and turn them into indexes, different kinds of indexes. So this tokenization step would maybe be different for when we're building terms than when we're building K-grams, right? And it would certainly be different when we're building phrases. That would be sort of a different kind of search process in itself. But those are all the steps we take before we build our primary indexes. Then, as we've discussed the past couple of times, we can do some secondary indexing, which will allow us to build some search systems on our search system, right? So we can build a system of searching for terms using K-grams, right? We saw that was useful in wildcards, but also spell check, right? Or soundex to terms, right? So we can have a system, we can build an index that can search out terms based on their soundex form that helps us, capture the phonetics, capture the way that these words sound, right? So this is the suite of indexes that we have discussed so far. There's more possible, and there's certainly lots of different ways to use all of them. And again, we won't be covering every single depth, but this is a pretty healthy set because this allows us to do quite a lot of good stuff on the other end. So remember, we've built our information retrieval system. Now we need to actually be able to process queries, right? So from the information need end, from the user, we get their user input. And then we might stop off and work a little error correction, right? We might say, these terms don't seem to exist in my indexes. Let me go consult the k-gram term index and do a little edit distance questioning and find, the k-gram overlap and all the things we talked about last couple of times. And then I'll find a better term. Okay, so we process the user input through some error correction using our secondary indexes. We can also do query expansion with things like wildcards, right? So we say, oh, well, they've designated this wildcard. I might need to go and dig around for other terms that will help me make sense of this. So query expansion, it also takes in our secondary indexes and it says, hey, I'm going to get multiple terms for you. Resulting in, so the user has input some kind of basic query, we've maybe corrected some of the terms in it, and we have expanded any queries that exist, or any terms, any wildcard type terms that exist. And now we're ready to do that thing we did at the very start, is the Boolean search, right? We're going to pull out the postings from the primary indexes using our expanded and corrected query. And also, we're going to find the postings for documents of all the terms, of all the phrases, of all the expanded queries, all that good stuff. Wonderful. Except, we're not done. Because before we show this set of documents that we found to the user, we need to do another big step. We need to sort them for them. We need to try and arrange them in a way that is going to satisfy their information need. We're not going to get beehive sadness on page 1 of my search, or rather the Amy Winehouse on page 1 of my search, if we don't do some sorting and trying to capture how relevant is each document in my result to the information need originally. So, we've made a lot of progress so far. Looking back at that, I hope you feel it. I hope you realize it. I hope you internalize it, that we're getting really close to a fully functional information retrieval system. But we still have to tackle that last pretty big step. How do we actually rank results to make them useful for fulfilling information needs? So that's the goal of today. We're going to start getting into how these search results ranking systems work. There's a variety. We'll talk about a really cool one next time, but we'll talk about some baseline good stuff to start. So, again, just to kind of double back, we up until now we've it's all been unstructured data in the form of the documents, and we created indexes. And now we're able to take some information needs and run them through the index to get results, right? But we've only been doing that in the Boolean retrieval sort of way. Looking back at our indexes, we've got the big pile of them, right? We've got term document indexes for basic terms. We can do some strict lexical search using k-gram document indexes. We can do wildcard expansion using the k-gram term index. We can do some phrase searching using either phrase document or positional term document indexes. Spelling correction using k-gram term indexing and a little bit of extra processing like edit distance, cards, all that good stuff. And then phonetic correction using a soundex term index, right? Handful of features that we're able to offer. But when it comes down to it, our results page so far is only ever going to be able to just kind of say, here, you deal with these, right? Well, we haven't done any kind of arranging of what's on the results page, right? The results page is what we would construct, but rather the results that we get, right? After we've gone through all the process of intersecting postings and finding the correct set of documents, we haven't done anything to sort them in a way that's meaningful for the user. There's no priority. There's no ranking, right? Ranking being the big thing here. So what we need is a way to take these documents and evaluate their relevance to the information need. Ultimately, which one of these is my user actually going to want? So for ranking a set of results, what we're trying to figure out is what is the strength of the relationship between a given query and a document, or any given document, each and all of the documents, right? So, of course, when it comes down to it, the only way you actually know this for a person is what they tell you, right? The user is going to figure out if their document is actually relevant. We're not dealing in absolutes of finding the most relevant guaranteed. Our system can't do that. It's not a whole person. It doesn't have the capability of pattern matching everything the person's looking for. Because honestly, sometimes even the person isn't quite sure what they're looking for, right? So the idea is that we can using some techniques, we can get our system to take a good guess, get closer to giving the user a relevant set of documents. So what do? We need some kind of numerical method for this, right? We need to be able to rank things. What can we do with our documents, with our tokens, with our indexes, with all of our queries, what kind of processing can we jump in and do to start measuring the ranking? So there's lots of ways. You can get some amount of relevance pretty easily. We have different types of indexes we can draw from, right? So maybe a document that matches on both your terms, the terms you've searched, and the kgram, the lexical, the order of characters, maybe it gets a point for both of those, right? So we have various ways that we can draw on all of the indexes available to us. We can look at the term frequency, how often terms occur, how close they are within the document. If we're drawing on our positional index, so if two terms appear close to one another, that might be good, right? That implies that they're a little bit more tightly related, at least in terms of the way that the query is represented in the document, right? Or we can get into some really kind of advanced, fun, wacky mathematical tricks that we'll talk about next time. And ultimately, all of these are useful. All of these are possible, and you can combine them. This ends up being kind of the special sauce of your search system is how do you choose to present the result list to your user, right? So today, we're going to talk about two specific kinds. Parametric and zone indexes, which we'll talk about, and then term frequency and weighting. So, let's get into them. So, parameters and zones. Parametric and zone indexes. Every document, no matter how much we think of them as just unstructured grab bags of words, right? There's always some kind of structure. It's structure that we can exploit and use. So let's look at some documents, right? We just mostly have been talking about them as a single string that you can split up into terms, and hey, then we're off to the index races at that point, right? But there's always a little bit more. There's always some kind of metadata about a document. What about green eggs and ham? Our old friend we've been working with this entire time. What kinds of metadata do we have associated with green eggs and ham? The book, right? It's a kid's book. It's got text, so we know the document text. Do you like green eggs and ham? I do not like them, Sam I am, right? He doesn't want the friggin' eggs. But there's other information here that we're not looking at yet. What about the title? What about the author? Still text. But it's fundamentally different than the document text. And in fact, titles might be a very good thing to give high priority, right? If we make indexes based on titles, that gives us a way to say, oh, wait, they searched for like, I found a title result for a document. I'm definitely pulling that up. I'll still pull up all the other document text-based stuff, but titles seem like they might have heavier weight, right? So, two kinds of metadata we'll be talking about here. Fields and zones. Ultimately, we don't need to really distinguish them heavily, but fields are a little bit more, they're closer to the very structured data that we would know from like database stuff, right? So these are smaller. They have things like dates, names, titles, page numbers, so they can sometimes be numerical, not just text. And there's only so much that you're going to be able to put in a field. I can't put the date in the author name field. That doesn't make any sense. That would be rejected by whatever system would be working with this. Zones are a little bit bigger, a little broader, and they still have that sort of unstructured feel that like the full document text. These are things like titles and abstracts and keywords, right? So if you've ever worked with an academic journal, these are going to be familiar. So we can handle them just like document text, but we can give them heavier weight if we think that they're more, they're the more relevant part of the document. So let's look at a journal article, right? Design it yourself, Surabaya, reflective notes on designing a festival. I don't even remember where I pulled this from. It's just a legitimately random document, right? If we were going to index this, we could tackle it a lot of ways. We could just kind of take all the text that we see and smush it into a term document index, and that would actually be fine. You can do that. But we can also work with all this available metadata. Here's the field, the title. The authors, or no, sorry, I guess the title is a zone. Authors are a field, a small set of very structured information. Author affiliations, what schools are they attached to? What research enterprises are they attached to? The DOI number, the exact number assigned to this exact document that identifies it across all journal publications in the world. That's probably a pretty good one to have around. If someone searches for a DOI number, you probably want to return the exact document, right? So that would be an index that would have very little recall, but it would be so precise. So if you did build a small DOI number index of your set, it would give people a direct route to, hey, it's like, hey, I know the exact paper. Find it for me. Now the abstract, right? If you've ever read one of these things, the abstract is like the short version of the paper, the sort of the elevator talk version of your paper. Like, I did this, we did this, we found this, and this is the big take home. That's actually pretty good, right? That could just be lumped in with the document text, but these are the things that the authors themselves thought were the most important parts. So maybe you give extra weight to abstract text. Keywords as well, those are also quite good, because that's what the authors have thought is most relevant. These are fields that this is relevant to. We can keep going. Journal title, volume number, journal title, volume number, the date that it was published, external links to other documents that cite this, documents that this cites. That's a lot. There's a lot of good information available here that we can split up and use separately. We could say these are all valuable. Some of these are going to have a lot more precedent, and some of them are going to be a little lighter, right? So fields, when you're working with this, fields and zones, they have this information that might be a little bit more relevant than your basic document text. And so by indexing these specific pieces of information, first of all, we give users more options. We could have them select, oh, hey, I know the author, but I don't remember the paper title, so I can't find it. So I'm going to say author, and then these couple of terms. So this is great. You know, even if we haven't yet gotten to ranking things, this is still powerful. So you could design your system to allow people to use just this, even just for the Boolean search side, right? So this is a little aside into, hey, we can even use this structured bits of metadata to help with even completely unranked search, still make it good. So here's my information need in this little example. What was that Beatles song? Definitely like late 60s. I remember I am something something. Super weird. Everyone remembers it's weird. Oh, dang it. If you just said I am Beatles late 60s song into a search engine, it would probably just get a bunch of back catalogs of magazines, right? Those are just words that are going to show up together in old documents about this. But if I'm trying to get this exact song, well, I can achieve that by specifying things about the fields that I actually do know, right? I know the artist is the Beatles. I know the year is probably 66, 67, 68, or 69, so I could, I can input those into the search. I know the file type is a song. I'm not looking for a text document here. And I know the phrase I am is somewhere in the lyrics. So this ends up really narrowing the field, really enabling the user to take what they actually do know about their document that they are in search of and specify it so that we can really narrow down the Boolean search until we get, there's only really one song. It's I Am the Walrus. Again, it's kind of a weird song. You should look it up if you haven't heard it before. It's mostly gibberish and LSD, but that's life in the 60s. So this shows that we can use I hope this illustrates the power of these different fields, right? They are key to understanding what the document is, right? And it brings us closer to the information need. So you can also see this if you're doing like a bibliography search. If you are trying, perhaps this is a little outdated for this exact library, but these are the kinds of search systems you encounter where you can specify a lot of specific things, right? And these interfaces are okay. These are good to have around for the user. But this is still not getting into the sort of complex mental gymnastics that we would have to pull off to figure out okay, even if they've narrowed it down to 20 documents, which one do I show them first, right? This is still just Boolean retrieval. So we can get into an exercise called weighted zone scoring. I don't mean exercise. I mean this is a process. But the idea is that, okay, apart from making the user specify the exact things for the Boolean search, we can also go ahead and just automatically figure some of that out, right? So we can use fields and zones to give extra weight to a document's score if the user's just kind of smashed a bunch of words in and it hits some of these things. So this begins our trek into ranking proper. So say we have just the basic query, I am the walrus, not I am the walrus, right? If we're just looking for those exact words, we're probably looking for the Beatles song, right? That seems like a reasonable thing. So how do we get there, right? How do we compute, this user entered the two words the and walrus. How do we do some computation using the different zones to bring the walrus, I am the walrus, to the top of the pile? So how might we compute a weighted zone score? Let's say our documents all, in our collection, the way we've defined our collection, our documents have 3 fields every time. The author, the title, and the body, right? We've limited this. A lot of documents have more, like we discussed, but we can just say, for our search system, we got author, title, and body. And in this case, if it's for songs, body is probably going to be lyrics, okay? So we can give each field some amount of weight, right? A number that we will multiply the result of. So we'd say, it's between 0 and 1, right? So that all the weights will add up to 1. So what we're saying is there's going to be some computed weighted value of each result based on whether our search terms show up in each of these. So for every field or zone in the document that matches the query, that document gets points, right, in its ranking computation. So for the fields, author, title, and body, let's say we give author a weight of 0.3, title a weight of 0.2, and body a weight of 0.5. That's a total of 1, right? For each match in a document's field, we're going to add the weight to its score. So then we sort all the resulting documents by those scores. So let's do that. Query, the walrus. The fields are title, author, and body. The weights are 0.3, 0.2, and 0.5. Let's look at some documents. Document 1, I am the walrus. Author is the Beatles. Okay, that's fine. That doesn't match at all. The Eggman, I am the walrus. Oh, shoot. So it's also in the body. Great. Document 2, walrus mating habits. Okay, this is by David Attenborough. The walrus is among the... Okay, so that only gets the 1 hit, right? The body has matched properly, but it's not in the title. So the document 1 has matched both the body and the title, so it gets a score of 0.8. And document 2 has only matched the body. It gets a 0.5. So in this case, because there is something in our collection named with the walrus in the name, those are all going to percolate to the top immediately. We still haven't done much other searching, or rather other sorting, other ranking on this set of possible documents, but we have bubbled up everything with the walrus in the title. That's pretty key. So this gives them priority, right? This is a way of giving certain documents some priority. This is good too because we could also handle partial matches. So document 2 contains only walrus and not the, so we can give a little bit of the weight to it, right? So we can, how you choose to do this, if you were going to implement it, allows you to make it a little more fine-grained, a little bit more sensitive to the variations, right? So the question ends up being, how do you actually sort out what the zone weights should be? We just did it. We just kind of hand-picked them, right? It's easy enough to just like tweak and adjust them and see how it works, but that requires you to be on top of it. You can also let the user specify them, but that's a little bit tweaky. That's a little bit like extra effortful on the user's part that we don't necessarily want to throw this on their plate. They'll just go and use a different system if we make ours too finicky. You can also automate it with machine learning. So let's take a little aside into machine learning. So in machine learning world, what's the basic idea? We are giving the machine an algorithm so that it can learn something on its own, not given just an exact instruction set from us. So what we can do is you can continuously update the settings, the field weights in this case, based on feedback from a training set. So a training set would be a set of queries and goal documents that contain both relevant and irrelevant pairs, right? So a query might be matched against a bad document, and the training set would say, hey, human beings have told us that this is a bad document. So I'm going to show you this, and you're going to guess, and I'm going to update you. So, and this is, again, it's based on actual user data. So let's look at this. Oh, there's a lot to pick apart here. So document ID 37 and the query being Linux. This for this document, the score for title is a match, right? So S sub T, that's a match. And S sub B for body, that's a match too. Okay, so the idea of this search is we're going to try and figure out what should the weightings be for title and body. And in the real world, the way this data was pulled in, people judge this document to be relevant. So document 37 is relevant to the query Linux. Human beings said that. So what you can say is, oh, good. So the algorithm that I have right now with the title weight being 0.5 and 0.5 was good. It did a good job. I don't need to change it. It said, humans said, oh, that was relevant. Okay. Now, what about penguin? If I search penguin on document 37, this document that people have judged to be relevant to Linux, it doesn't match the title, but it does match in the body somewhere. But humans have judged it to be non-relevant. So what we'll do is we'll say, ooh, shoot, I pulled this document up, I being the algorithm, right? And just anthropomorphize it. I pulled this document up, but it only matched on body, and it was bad. It seemed like it was bad. So maybe I shouldn't weigh body as much in this collection. So we punish the body weight, so that goes down to a 0.4 weighting, and we upgrade the title weight because we got to fill in the gaps. So great. Then we have another match, so or another query, right? System for document 238. We're on a different document now. Because remember, we're trying to build the system to be document agnostic. We're trying to build this process to do itself, right? So system in document 238 didn't match the title, but did match the body. Oh, shoot, the user said that is relevant. And the title part didn't matter. So I'm going to bump body weight back up, right? And we're going to keep going. 238, penguin didn't match at all, so it didn't even come up, and the user said it was not relevant. I don't need to adjust anything. This is just a smidge. This is just a taste of a lot of how machine learning generally works. It takes examples, and it updates its internal numerical system to say, okay, based on what I've been shown, I think this is the appropriate set of weights to use. So this is a very simple application, but the idea is just to illustrate a little bit about how this works. And you might be able to get a peek here of how the Google algorithms these days, the Facebook algorithms of these days, can take user activity data. So, if you click something, that's inherently, hey, at least it was sort of relevant. And it's going to tweak itself. It's going to adjust itself. It's going to train itself saying, oh, well, the thing that you click, that means that it was good, so I'm going to keep doing that. I'm going to update my internal setup to do that. So that's machine learning, just an aside on how you might design a system and how you might choose this sort of a big problem of, how am I going to set my field weights? So this is sort of the structured data way to tackle how relevant is each document to me. There's additional metadata here, right? It's not just the body text that we can actually use. And we can index them, right? We can index them for customized Boolean searches, but also use those indexes to say, hey, I got to match here, here, and here, but not here. Rank that. You can use that to rank, right? So this is great. It helps narrow search, but it also, it gets into relevance. The title is often much more relevant, right? But we do have to decide how to set the weights. And whether we want to do that with a training algorithm or with our own just custom tweaking it or whatever we want to do, that's fine. We can do that. But just the idea here of this is where systems like this can kind of get into solving that problem for us with machine learning. So that's fields and zones. We can also take an unstructured approach to this, which is quite nice. That's one of the things we like in this world we're talking about, right? And we can get into term frequency and weighting. So, one way we might make sense of whether or not a document is relevant to our search is looking at the term frequency. How often does this term show up in our document? This document has the term walrus 50 times in it. This document has the term walrus once in it. You could see maybe that there are two different levels of engagement with the query, right? So, first, to be able to achieve this, we'd have to actually track term frequency. This is something I mentioned way back as one of the things we might double back to do, and when we build our indexes, we might actually want to keep track of term frequency. And so we shall. So, the idea here is that term frequency is how often does something appear in a document? How often does one of our terms appear in each document, right? And this is, we get it for free if we're tracking the positional indexes, which is super nice. Maybe that's a good reason to build one. Haha, wink, wink. So, term frequency would just be the number of positions that you've actually stored, right? If we're already going to store the numerical values of the positions of the terms in the document, we can also store their frequency, or we have implicitly stored their frequency. How often, how many times did it occur? And this is also something called the bag of words model. We don't care about the order of the words when we're tracking term frequency. When we're tracking, just doing this sort of basic, we're trying to rank the document, right? And when you do term frequency, you don't even see whether or not the terms are in the same order. All you know is how heavily they show up, right? So we're converting our terms a little bit even further, more abstracting away from their position in the document and more just turning them into a number. So let's look at this. Query term is walrus. Document 1, the Beatles song, right? I am the walrus. In the title, repeated in every course, right? Only a few times. Versus the nature article, walrus continuously referenced throughout the entire body of the text. It happens 50 times. Term frequency is going to favor the nature article for having walrus mentioned far more often, right? That's good. That's how we should do it. Now, if I add the word the walrus, well, now that should maybe alter things a bit, right? If I did a phrase search for the walrus, that's going to show up tons in I am the walrus. It's maybe not going to show up quite as much in the nature article, right? Because the is not often, it's not often the walrus, right? It's often a walrus or walruses or whatever. That's all material, though. This is sort of just off the cuff. So that's the basic idea. That's all it comes down to. So given these two documents, I could tell you pretty certainly, if you just searched for the word walrus, yeah, I'm going to throw you a bunch of nature articles. Of course I am. Because those are the things that reference walrus most often. And if I'm combining this with with field and zone weightings, I'm going to get a bunch of things with walrus in the title. I'm going to get a bunch of documents with walrus repeated in them multiple times, so we're getting there. We're getting to a way to sort and rank our search results. Okay, but there are some issues with term frequency. Not every word is equally important. So if I'm just doing a normal the search, why is the word the useless in search? So useless, it's like on most stop lists, right? Obviously, again, in the phrases you might be helpful, but the is nothing because the shows up in every document on the friggin' planet. English document, of course. The doesn't help because the has a incredible document frequency. So not just the term frequency of how often it occurs in a given document, but also its document frequency is through the roof. Whereas walrus is less common, right? it shows up in way fewer documents than the word the. So walrus is less frequent across documents than the word the. This is useful information because this is showing us that one of these words is way more informative about the search than the other. This brings us to inverse document frequency. So this is a way to assign the importance of rarer terms as opposed to giving terms that are more rare higher values than frequent terms. So we can calculate this using the document frequency. And in terms of our indexes, right, because that's all we really have access to when we're building our system, that would be how many postings are there for a given term, right? So not necessarily the number of times a term occurs for one given posting to a document, but how many documents is the term in? You know, if green eggs and ham, right? We'll look at that later. But the idea is that if we have a collection, right? We have a large collection size. We also take the log of this value. So the big idea is I'm going to take the collection size, I'm going to divide it by the number of documents with this term, and I'm going to take the log of that. So if this is a huge document size, if this is a large collection, say we have some number, and if this thing shows up in very few documents, that's going to be a big value. If it shows up in all documents, that's going to be 1 over 1, right? It's going to be 10,000 over 10,000. That's going to be almost no value at all. So, and also logging, the log transformation gives some special properties to the math that make it easier to use it as a scaling factor. That happens a lot when you're dealing with math. Logs are just kind of nice ways to convert things into a slightly more natural numerical way of thinking about things. We don't have to get into that. It's an interesting property of human brains too. But yeah, so let's look at how to handle inverse document frequency, right? So IDF, that's what this is. So we're going to take the log of the collection size over the number of documents with the term. So 100,000 documents, 10 documents with the word capybara, 90,000 documents with the word cat. Okay, let's work through capybara. What is its IDF? Well, 100,000 over 10, that's 10,000. Cool. Log of 10,000, at least if you're doing the base 10 log, is 4. Nice. Okay. So the IDF, the rarity of this term, at least within our collection, is 4. What about cat? Well, 10,000 divided by 90,000 is 1.11. The log of 1.11, the log 10, is 0.457. That's a very common term. This is good. This gives us a way to scale. Hey, this is a very frequent term. It's not very important in this collection. Whereas this very infrequent term, I'm going to need to handle this. So the rarer term gets higher IDF scores. This is great. This gives us a method for calculating all of this. So to recap that, inverse document frequency, the less frequent terms are more meaningful when they appear, right? It's more useful. It's more informative. So information theory, right? It's more signal when a document with a rare word appears. And the inverse document frequency gives us a way to quantify that rarity and help scale back frequency of kind of less interesting terms, right? So car, for example, is more frequent than the term auto, right? And so if I have a match on the word auto, that's maybe a little more important, right? That's maybe just a little bit better indicator of what kind of document I'm going to come to, right? A little bit more academic, a little more technical document about cars versus just the word car. And both of them are fine. You see that their IDFs aren't wildly far apart, but they're both useful. Or rather, one of them is slightly more informative when it shows up. So, how do we use this? This is called TF-IDF. The term frequency is how often the thing shows up in the document, and the IDF is how often that term shows up across all documents. So, how common is this term? Or rather, how rare is this term, to keep it in the same direction, multiplied by how often it shows up in the document. So when you combine them, it gives us this great metric all wrapped up in one little number. How relevant is this number of term matches in this document given how often it appears in this collection? That's great. So, simply put, to get TF-IDF, you multiply term frequency by IDF. Let's do it. So, this will be a little more general. Description. This is a word that occurs many times, but it's an infrequent word. So, walrus in like a Nature article, right? Its term frequency is high, and its IDF is also high. This is going to get a pretty high score, right? This term occurs a lot in this one document and not much in other documents. That means this document is a good match for the information criteria here. So TF-IDF would be something like 80. How about few occurrences but infrequent? Well, that's captured well by, walrus of the Beatles variety, right? So the term frequency is less than it was, but it's still got a pretty high IDF, right? It's still rare across all documents. So this is still a good match compared to something that was far more frequent in the document, like the. This word is still informative. It's less informative than the other document because the other document mentions it more often, but it still percolates up, right? How about many occurrences and a frequent word? So cat will have a term frequency of 20, say. It happens a lot in the document, but in this document collection, it's a very frequent term, so it gets scaled back, right? It's not as uniquely informative as walrus. So it ends up with a TF-IDF of something like 8. And then we can look way down at the, right? So many occurrences, extremely frequent. So, okay, just because the shows up 200 times in my document doesn't mean it matters because it shows up in every friggin' document. So its IDF is way low. It almost every document has this word in it. You multiply those together, you end up only with about a score of 0.1. So that means the is borderline useless, and that's why it doesn't kind of factor into a lot of these searches. So, TF-IDF is highest when an infrequent term also appears often in your document. It will lower a bit in either case when the term either occurs a little bit less in the document or it occurs in tons of other documents too, right? It's a little less informative. And it's extremely low when a term appears in almost all documents. It approaches 0, right? So it almost makes it so that term becomes useless. Couple notes. It's reasonable to assume that a document that has the word walrus 20 times is not 20 times as relevant as the document that mentions walrus once, right? There's this factor of, as I mentioned before, kind of a log linear vibe to a lot of these things. There's diminishing returns, right? You are not going to get... It's not 20 times as relevant. It might be twice as relevant for being 20 versus 5, right? So longer documents don't need to be valued more just because they mention the word 700 times in a row. So, but we still want that sort of natural, like, okay, this is a document that's mentioning this stuff a lot. So, kind of cap it off, make it curve it so that it's a little less. That's what the log is for, right? So again, we can take the log of term frequency to make it a little bit more, a little smoother, right? Because if the thing shows up once in a document, that's still really informative. If it shows up 5 times, that's probably a lot more. But then the difference between showing up 100 times and showing up 1,000 times, like, okay, we get it. These are both fully about this topic, right? So the log transform makes it so that, say, for example, if you're doing a log 10 transformation, if something shows up 10 times as often, it's only going to be considered twice as relevant. That's fine. That's good. We don't need to, this is something that you can switch on and off very easily. It's just a single mathematical operation to transform these things, but it's useful. It's good. I think it's healthier when you're thinking about natural language and natural text to think a little bit more log linear than linear. Okay, anyway, moving forward. How do we use this? How do we take this stuff that we've learned and actually apply it to a query? Well, this is big. This is a big point. This is actually how you would do this. This is what you would do here. You would compute the TF-IDF overlap for each term in the query. So the idea is that after your Boolean search goes through all the trouble and gets us, intersects postings and finds documents that are viable, now we have a set of documents. So for each one of these documents, we can run through and say, okay, what is the TF-IDF overlap of this document for each term, right? Or rather, what is the TF-IDF score of this term in this document? And then we're going to do it for each term, and we're going to sum it all together. So basically the idea is each document will then have some score based on the number of occurrences and the rarity of the terms. So let's look at this. So what's the actual computational process? So for each result document, you're going to look at each query term. And first you ask, okay, what's the inverse document frequency of this term across my whole collection? And that, again, you calculate just by snatching out of the index, how many postings does this term actually have? Then similarly, we get the actual term frequency of that term in this document, which again, if we're using our positional index, is pretty easy. We just ask, hey, how many positions exist for this posting for this term? Using those two pieces of information, we compute the TF-IDF score for that query term. We do that for all the query terms, and then we sum the results. So looking at two of our quick examples we've poked around in, Beatles document, right? The TF-IDF, that the value for that is going to be super frequent word, right? But it's going to happen fairly regularly. It's going to end up with a very low score, right? So the TF-IDF of for our query, the walrus, is 0.1. But walrus, it's still an infrequent word, so its IDF is going to be high, but it only shows up a few times. So let's assume it ends up with a score of about 10. So the TF-IDF overlap of the Beatles document with the query, the walrus, is 10.1. The nature document wins out because it's achieving, it's getting happens a little more often, even though it's a less frequent, it's still a very frequent term, it's a less valuable term, it still adds a little bit more, but really the thing driving this is walrus is still an infrequent term, but it's showing up everywhere. Or rather, it's showing up quite often in this document, right? So it ends up with a very, very high TF-IDF score. So it wins, right? The nature document ends up with a higher TF-IDF value than the Beatles document. They're all still going to win against other documents that occasionally mention these things, like one off, at the end of some article on, it's an editorial or something where they call someone a walrus or something, right? These both are still frequently using the term. It's just that the nature document uses it quite a lot more. And in both cases, the word "the" is kind of irrelevant, right? Okay, so we've gone on quite long here. I'll wrap it up here. We've taken two different looks at the way scoring works, right? We can work with zones and fields, right? So this structured data that's available in almost every document want to be working with. And we can build indexes on those things. It's totally fine to do that. It's powerful to do that. And in fact, it makes search more flexible even just at the Boolean search level. The user can specify things like we've seen in certain library search systems. And we can also use it to do the scoring, the ranking scoring, as long as we know what we're doing with the field weights. But we can also do this sort of ad hoc, this sort of not prescribed, not structured way, just based on the grab bag of the words that are available in the documents. And we can get TF-IDF to tell us how frequent are the rarest terms in this document. So, ultimately, you can keep working this, these are multiple tools in the belt to help address the question of how do I get my user my search, the search that they want, the result that they want. So matching on fields is just kind of smaller indexes of smaller sets of our same documents, right? And we can include other indexes, right? So as I mentioned before, we can look back at the K-gram matches. We could say, hey, oh, this thing matched on the K-gram lexical character order search as well. That's kind of useful. Oh, this thing auto-matched on a phrase. I didn't even know I was looking for a phrase. They didn't specify a phrase, but I found the phrase. The phrase was in my phrase index. That's also powerful information. That could give a very large boost because it's very specific, right? So that's just a look at how these things you can just kind of keep pushing, right? You can take these same ideas of getting sort of the word-based relevance, the sort of linguistical relevance, and the more metadata relevance based on multiple matches on multiple indexes. All right. Next time we'll talk about, I think, one of my favorite pieces, the vector space model. It's another way of kind of extending this. How do I convert words into numbers, and then how can I do some fun math on those numbers? But for now, final thought. How frequently do you find yourself including very frequent words in your searches? Have you ever felt that they actually did help? If so, how might that work? If not, why didn't it? All right, thanks. Take care.